Hi, my name is Dan Abel, and in this lesson we're going to calculate the internal resistance of a battery. Ideally, batteries and wires in a circuit should have zero resistance to current flow. However, in real circuits, batteries, just like wires, have a small resistance due to their metal and chemical component. The fact that batteries get warm after use is evidence of this internal resistance and the energy that gets dissipated as the current flows through the battery. Thus, a real battery is best thought of as an ideal battery in series with a resistor. And so, what we see here is the ideal battery with the script E is our EMF. That would be the 1.5 volts, for example, that's stamped on the side of a AA battery. And then the resistor R represents the internal resistance of that battery. And we can calculate the actual measured voltage by taking the stamped EMF, the 1.5 volts if it's a AA battery, minus the voltage drop across the internal resistance of a battery. So using Ohm's law, the voltage drop will be equal to current times resistance. As a real battery's energy is depleted, that resistance R grows and results in a reduced voltage measured across the battery terminals. And at some point, that voltage gets low enough that the battery is then considered dead. This is why some flashlights will dim before they completely go out. As that battery's internal resistance grows, its terminal or measured voltage starts to shrink and it can no longer drive as much current through the flashlight bulb. Let's see an example of how you would calculate the internal resistance of a real battery. In this problem, we got a 4.5 volt battery connected to a 3 ohm resistor, causing 1 amp of current to flow. And we're asked to find the internal resistance of the battery. In this case, we're going to go back to Ohm's law, V equals IR, and we're going to plug in the values that we have. Now, if this were an ideal battery, we should have 4.5 ohms of resistance in the circuit. But in our case, we only have 3 ohms. So the other 1.5 ohms must be coming from the internal resistance of the battery. In a future lesson, we'll learn that when we have resistors in series, the total resistance, in this case 4.5 ohms, is the sum of each resistor in the series circuit. So the takeaway here is that early on in a battery's life, the internal resistance is small enough that the measured voltage is fairly close to the EMF that's stamped on the side of the battery. However, as time goes on and that internal resistance grows, eventually the measured voltage becomes low enough compared to the EMF that we have to consider the battery as dead and replace it.